Hello everyone, Mr. Navarrete here, and today I'm going to be going over Lewis Dots homework number 1. So let's just jump in. For part 1 it asks, draw the electron dot structure of the following atoms. So for our first one, we have potassium. Potassium is in the 4th period and in the first group, so that means it's going to have 1 electron in the furthest shell, or 1 valence electron. So I'm going to draw my chemical symbol, K, for potassium. And then I'm going to add 1 electron. It doesn't matter on what side you place it as long as it's not in the corners and you only draw 1. Let's move on to our next one. Next, we have phosphorus. Phosphorus is in the 3rd period and in group 15. So that means it's going to have 5 electrons in the furthest shell. 5 valence electrons. 2 from the s orbital and 3 in the p orbital. So I'm going to draw my chemical symbol for phosphorus, P, and then I'm going to add 5 electrons. Now, we have to remember Hund's rule, where we have to fill up every sublevel before doubling up. And in this case, we have to fill up every side before we can start doubling up valence electrons. So, 1, 2, 3, 4, and now I can start doubling up 5. And that's it. Moving on to our next one. Here we have iodine. Iodine is in the 5th period and in group 17. So that means that it's going to have 7 electrons in its furthest shell, or 7 valence electrons. 2 are going to be in the s orbital, 5 in the p orbital. So I'm going to draw my chemical symbol for iodine, which is I. And then I'm going to add 7 electrons. Remember, we have to fill up each side before we can start doubling up. So 1, 2, 3, 4, 5, 6, 7. And that's iodine. Next up, we have calcium. Calcium is in the 4th period and in group 2. So that means it's going to have 2 valence electrons in the furthest shell. 2 are going to be in the s orbital. So I'm going to draw a chemical symbol for calcium, Ca, and then I'm going to add the 2 electrons. 1, 2. I'm drawing them as far away from each other as possible, and we can't start doubling up until we fill all of the other sides. Let's move on to our next one. Next up, we have gallium. Gallium is in the 4th period and in the 13th group. So it's going to have 3 valence electrons, or in the furthest shell. 2 are going to be from the s orbital, and 1 is going to be in the p orbital. So I'm going to draw a chemical symbol, Ga for gallium, and then I'm going to draw the 3 electrons. 1, 2, 3. And again, we have to fill up all of the other sides before we can start doubling up. Next up, we have beryllium. Beryllium is in the 2nd period and in the 2nd group. So that means it's going to have 2 valence electrons. 2 from the s orbital. So, same thing, drawing the chemical symbol. So, Be for beryllium, and then add the 2 electrons. And again, we can't start doubling up until we fill all of the other sides. Moving on to our next one, we have sulfur. Sulfur, 3rd period and in group 16, so it's going to have a total of 6 valence electrons. 2 from the s orbital, 4 from the p orbital. So, same thing, drawing my chemical symbol for sulfur, which is S, and then adding my 6 electrons. 1, 2, 3, 4, 5, 6. Next, we have cesium. Cesium is in the 6th period and it's in group 1, so it's going to have 1 valence electron and in the s orbital. So I'm just going to draw chemical symbol for cesium and add my 1 electron. Moving on to our next one, here we have xenon. Xenon is in the 5th period and in group 18, so it's going to have 8 valence electrons. So I'm going to draw my chemical formula, C, and then I'm going to add my 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Lastly, we have bismuth. Bismuth is in the 6th period and in group 15. So it's going to have 5 valence electrons in total. I'm going to draw the chemical formula for bismuth, Bi, and then add my 5 valence electrons. 1, 2, 3, 4, 5. And there we go. Awesome. Let's move on to part 2. For part 2, it asks to draw the Lewis dot structures of the following molecules. And for these specific questions, they're all going to follow the octet rule. So we have an iodine molecule. So what I'm going to do is I'm just going to draw iodine, draw them like this. 1, 2, 3, 4, 5, 6, 7. That's one of them. And then the other one is going to be 1, 2, 3, 4, 5, 6, 7. Now our goal is to kind of make them fit in a way where both of them are going to have 8 electrons. So what we can do is move them together like that. And now one iodine is going to have 8 electrons. It's going to have a full octet. And the other iodine is going to have another full octet. So they're both going to be happy, and they're both going to be following the octet rule. Here we have methane, CH4. So carbon is going to have 4 valence electrons. And just get that from my periodic table. And we have 4 hydrogens. So 1, 2, 3, and 4. Each hydrogen has 1 valence electron. So I'm going to just move them over. It's kind of like a puzzle. And seeing where all of them fit. And here we go. Carbon now has 8 valence electrons. It has 8 electrons in total. And each hydrogen has 2. Now, remember, hydrogen is in the first period, and that first period can only has that one s, or that first s orbital, so it can only hold a maximum of 2 electrons. So hydrogen is going to be happy because it has a full shell, and carbon is going to be happy because it has a full shell. Here we have calcium tetrachloride, and very similar story. Carbon is going to have 4 valence electrons, and chlorine, each one has 7. 1, 2, 3, 4, 5, 6, 7. The other one's Cl. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 7. Again, it's just moving them around and trying to find a placement where they're all happy, where they all have a full octet. So, I'm gonna move this one here, this one here. There we go. This one there, and this one here. Cool. Each chlorine has 8 electrons now, so they're all going to be happy. And carbon is going to have 8 electrons, and it's going to be happy. They're all going to be following the octet rule, so that's it. For our next one, we have ammonia. Nitrogen has 5 valence electrons, like in my periodic table. So 1, 2, 3, 4, and 5. And each hydrogen is going to have one valence electron. So again, just like a puzzle, trying to see where they all fit. And here, nitrogen, it's still going to have 8 electrons, so it's going to be happy. And hydrogen, again, because it can only, its shell can only fit 2 electrons, is going to be perfectly fine. So all of these are going to follow the octet rule. So here we have hydrochloric acid, just like our previous examples. Hydrogen is going to have 1 valence electron, and chlorine is going to have 7. 1, 2, 3, 5, 6, 7. And now we just find a way where they fit. Hydrogen is going to be happy with 2. Chlorine is going to have its 8. And that's going to be it. Next we have phosphorus trichloride. Phosphorus, again for my periodic table, is going to have 5. 1, 2, 3, 4, 5. And we're going to have 3 chlorine. So each one is going to have 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, and then 1, 2, 3, 4, 5, 6, 7. And now we just gotta move them. And that is our dot structure for phosphorus trichloride. Here we have H2O, water. Hydrogen is going to have 1 valence electron. There's 2 of them. And oxygen is going to have 6. 1, 2, 3, 4, 5, 6. And now we just move our puzzle pieces. And that's our dot structure. Move on to our next one. Here we have nitrogen trifluoride. Nitrogen is going to have 5. So 1, 2, 3, 5. And we have 3 fluorines. Each one's going to have 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 5, 6, 7. And just gotta move our puzzle pieces. Each fluorine is going to have its 8. And nitrogen is going to be happy because it's going to have all of its 8. For our next one, we have silicon tetrachloride. Silicon, looking at it in the periodic table, is going to have 4. 1, 2, 3, 4. And then I'm going to have 4 chlorines. 1, 2, 3, 4. And each one is going to have 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 6, 7. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 6, 7. And now we just gotta move our pieces around. So I'm gonna move this one here. move the whole thing down because I can fit more. This one there, and this one here. And that's our dot structure. Each one is going to have 8 as well as our center one. Here we have a fluorine molecule. Fluorine is going to have 7. 1, 2, 3, 4, 5, 6, 7, and the other one 1, 2, 3, 4, 6, 7, and moving our puzzle pieces. Each one is going to have 8. And that's exactly what we want. Here we have carbon difluoride diiodine. Carbon is going to have 4 valence electrons. We have 2 fluorines. Fluorine 1, 2, 3, 4, 5, 6, 7. Each one is going to have 7. 1, 2, 3, 4, 5, 6, 7. And then we have 2 iodines. And each one of those also has 7. 2, 3, 4, 5, 7. 1, 2, 3, 4, 6, 7. And now we just gotta move them around. And let me just kind of. Now you could definitely flip the arrangement of your iodines and your fluorines and have them flipped and kind of change the pattern. However, when we start talking about models, specifically VSEPR models, and how each of these atoms wants to form a very stable form, this one would be the most favorable as their electronegativities create a non-polar molecule. Here we have phosphorus trihydride, and phosphorus is going to have 5. And we have 3 hydrogens. And each hydrogen is going to have 1 valence electron. So, I'm just moving our pieces around. Oh, took a little too much there. And each hydrogen is going to be happy with 2. And phosphorus is going to have 8, meaning it's going to have its full octet. Here we have ethane, or C2H6. Carbon is going to have 4 valence electrons. We have 2 of them. And we have 6 hydrogens. And each one is going to have 1 valence electron. So now let's move our pieces into place. This one might take a little bit more time since there are a lot more pieces than we're used to. However, it'll still give us a structure where everyone is happy. Each carbon is going to have 8, and each hydrogen is going to have 2, meaning every single atom in here is going to have a full shell. Last one for this section. For the last one, we have oxygen difluoride. Oxygen is going to have 6 valence electrons. 4, 5, 6. And each fluorine is going to have 7 valence electrons. 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And now we just got to move our pieces into place. Just going to center it a little bit more to have more room. And that's our structure. Oxygen is going to have 8, and each fluorine is going to have 8. Cool. Let's move on to the next page. On our back page, it says, these molecules will all contain multiple bonds. In this case, we have an oxygen molecule. Oxygen is going to have 6 valence electrons. 1, 2, 3, 4, 5, 6. We have 2 of them. And just looking at it, it might seem a little hard how each one of these is going to form an octet. If I move one oxygen over, seeing how many valence electrons it has, in total it only has 7. The other one also has 7. But if I move this electron over to this side, and I move this one over to this side, now when I move my oxygen, it can form a double bond. And that means instead of sharing only 2 electrons with each other, they're sharing a total of 4 electrons. Now, this oxygen has 8, and my other oxygen has 8. Both of them will have a full octet. Here we have a nitrogen molecule. Nitrogen is going to have 5 valence electrons. We have 2. Instead of keeping my structure like this, I'm going to rearrange some of the electrons. So it's going to look something like this. By arranging my nitrogen like this, I can see that instead of sharing only 2 electrons, they're going to share a total of 6. So each nitrogen is going to have a total of 8 electrons. In this case, we formed a triple bond. Here we have ethylene. Ethylene has 2 carbons. Each carbon is going to have 4 valence electrons. Each hydrogen is going to have 1 valence electron. So for me, what makes the most sense is, okay, I'm going to move my hydrogen here, this hydrogen here, this one there, and now this one here. However, when I look at how many electrons each carbon has, each one is going to have 7 here. To alleviate that, instead of forming a single bond, the carbon can form a double bond. Now, each carbon has a total of 8 electrons in its octet. Hydrogens only need 2. So they're all going to be happy. For our next one, we have acetylene. Carbon is going to have 4 valence electrons. We have 2 carbons. I'm going to have 2 hydrogens. And when I move some of my pieces around, doing this, carbon is only going to have, each one is only going to have 6. So instead of forming one bond, what we can do is that each carbon will share, instead of 1 electron with each other, they can share a total of 3 each. They're going to form a triple bond, allowing each carbon to have 8 electrons, a full octet. and hydrogen only needs 2. So that would be our dot structure. Here we have carbon monoxide. Carbon is going to have 4 valence electrons, and oxygen is going to have 6 valence electrons. We know that each one of these is going to form more than one bond, so instead of having them share just one electron with each other, I'm going to move one of these electrons over. I'm going to move this one over here. And keeping it like this, oxygen does have its 8, but carbon only has 6. So what can we do here? Well, oxygen is going to be nice enough to donate an extra pair of electrons to this bond. So instead of forming a double bond, they form a triple bond. However, we're still not done. Our electrons each still have an electronegativity, so to make things just a little neater, I'm going to rearrange them so that it makes the most stable form. For our next one, we have carbon dioxide. Carbon has 4 valence electrons, and oxygen, each one is going to have 6. For me, the easiest way to kind of put these together is have carbon as my center, and then have 1 oxygen on each side. By doing this, we can kind of see what next steps we need to make. Carbon is going to have 6 electrons. Oxygen is going to have 7 each one. So instead of this oxygen only sharing 1 electron, it can share 2. And this carbon, I can move this electron of carbon over here. The other oxygen will share another electron. And that electron from carbon will also move there. Carbon now has 2 double bonds on both sides. This oxygen will have 8. This oxygen will have 8. And my carbon will have 8. For our next one, we have tetrachloroethylene. And this one is going to be very similar to how we did number 17. Carbon is going to have 4 valence electrons. We have 2. And I have 4 chlorines. Each one is going to have 7 valence electrons. As I add my chlorines, it makes it a little bit clearer on what needs to happen with my carbon. See, just by simply leaving it like this, I can see that the carbon can form a double bond so that now each carbon has 8 electrons, that one as well, and each chlorine is going to have a total of 8 electrons. Each atom is going to have a full octet, and that's going to be our structure. Here we have hydrocyanic acid. Hydrogen is going to have 1 valence electron. Carbon is going to have 4 valence electrons. And nitrogen is going to have 5 valence electrons. What would be the best way to rearrange them? Well, I'm just going to use my carbon as my center. And if I move my hydrogen here, I can see what needs to happen between the carbon and the nitrogen so that they can each have a full octet. Let me just a tiny bit closer. This electron can pair up with another electron from the nitrogen, and this extra electron can pair up with another electron from the nitrogen. My nitrogen is going to have 8 in total, carbon is going to have 8, and hydrogen is going to have 2. They're all going to have a full shell. Now, just to make things a little bit neater, I'm going to move these electrons to this side. Here we have sulfur dioxide. Sulfur and oxygen each have 6 valence electrons. Sulfur has 1, 2, 3, 4, 5, 6. Oxygen 1, 2, 3, 4, 5, 6. And my other oxygen, I'll do it a different color. 1, 2, 3, 4, 5, 6. Here, I'm going to make the sulfur my center, and I'm going to put an oxygen on each side. Here, sulfur already has its 8, but oxygen only have 7. It's going to separate them a little bit. I'm going to move this electron over onto this side and this electron over onto this side. Now, so that I can form a double bond on each side of the sulfur, I'm going to have this electron go on this side and this one go here. Now, each oxygen has 8 and my sulfur has 8. Here we have sulfur trioxide, which is going to be similar to our other problem, but now we have an extra oxygen to throw into the mix. So sulfur has 6 valence electrons, and each oxygen is going to have 6 valence electrons as well. So we can tackle this problem very similar to how we tackled sulfur dioxide. We already know that sulfur dioxide formed a double bond on both sides with the oxygen, so we can just recreate that here. I'm going to move this one there, this one here, this one there. And just to make things a little bit neater, I'm going to redraw the structure to how we did with our sulfur dioxide. Now, if you're asking, well, each one already has 8, how are we going to fit another molecule in here? Well, the cool thing about sulfur is that since it's in the third period, it can hold more than 8 electrons. So if I move this oxygen here, it becomes a little clearer what needs to happen so that I can reach the octet. Each oxygen is going to have 8 electrons, and sulfur is perfectly fine with having more than 8. In this case, it's going to have a total of 12. So these extra 4 are going to go in the d orbital. This is one of the special cases, but there is a lot more than this. And that's part of our next section. For these next few, they're all going to violate the octet rule. Our first one is aluminum chloride. Aluminum only has 3 valence electrons, and each chlorine has 7. So when I move my pieces around, each chlorine is going to have 8 valence electrons, but aluminum is only going to have 6. And it's going to be perfectly happy like that. Why? Well, that's where you have to see what valence electrons actually are. See, aluminum only has 3 valence electrons, which means it has 3 electrons in the very, very outer shell. These 3 electrons let us know how many bonds it can make. Aluminum can only bond with 3 other atoms, and that's it. For our next rule breaker, we have phosphorus pentachloride. Phosphorus has 5 valence electrons, and we have 5 chlorine. Where do these all fit? Well, it's pretty easy to see that we can fit 1 chlorine there, another chlorine there, and 1 chlorine here. However, phosphorus is in the third group, so it can fit more than 8 electrons. It can do this by splitting. We can split this lone pair, and I can fit 1 chlorine here and another chlorine there. Let me move this one just a little closer. They're color-coded so you can see which electron belongs to who. Each chlorine now is going to have 8 electrons. And phosphorus is going to have, in this case, 2, 4, 6, 8, 10 electrons. 8 of which are going to be in the s and p orbital, and then the other 2 are going to be in the d orbital. Our next one is sulfur hexachloride. So sulfur has 6 valence electrons. And because it has 6 valence electrons, that means it can make a total of 6 bonds. So instead of drawing my sulfur like this, I'm just going to move some of the electrons space them out, and draw my chlorines around them. Each chlorine is going to have 7 valence electrons. And I know it might seem like some of them, like the chlorines, are bonding with each other, but they're not. Each one is just bonded to the sulfur. Each chlorine is going to have 8. And sulfur is going to have a total of 6 bonds, which would be 12 electrons in total. For our next one, we have borofluoride, and this one's going to be very similar to our aluminum chloride. Boron only has 3 valence electrons, meaning it can only form 3 bonds. Each fluorine has 7 valence electrons. So each fluorine is going to be able to fill its octet. However, boron will only have 6, and it's going to be satisfied like that. For our next one, we have beryllium hydride. Beryllium has 2 valence electrons, and hydrogen only has 1 valence electron. When we move our pieces around, here, hydrogen can only fit 2 electrons, so that one's going to be happy with a full shell. And beryllium only has 2 valence electrons, so it can only form 2 bonds. For our next one, we have a triiodide anion. And this negative charge does not mean that each iodine has a negative charge. It means that our whole molecule as a whole has an extra electron. So I'm going to draw my 3 iodines. Each one is going to have 7 valence electrons. Oh. And just looking at it like this, it might seem a little difficult to see where they can each piece together. But if I separate this bond just a little bit further away, I can move this iodide here and this one there. So now my whole molecule looks a little something like this. However, we do have that one little lone pair there. And that's where this extra electron plays a role. Because that means we're going to have an extra electron here. That way each single iodine doesn't have a lone pair, and only the center one has more than 8. To properly finish writing it off, we need to put it in brackets to signify that we do have an extra electron. Here we have sulfur tetrafluoride, and here sulfur, we know that it has 6 valence electrons, so it can make a total of 6 bonds. And to make it a little clearer to see where each fluorine is going to be bonded to, I'm just going to separate this pair just a little bit further away and have my fluorines bond at those points. Each fluorine has 7 valence electrons. Now with my structure, each fluorine is going to have 8 electrons, a full shell. And sulfur lets me do this because, again, it can just send those extra electrons into the d orbital. Here we have xenon difluoride, and this is probably one of the stranger ones. Xenon already has a full octet. So how can it bond to 2 fluorides? Well, if I separate, just kind of draw out this pair like this, I can fit 2 fluorines here. Each fluorine is going to have a total of 8. And xenon is going to have a total of 10 valence electron. And again, it can do this because it's in the 3rd period, and it can just move those extra electrons into the d orbital. Now, these aren't the shapes that it would take, but we'll learn about that once we start talking about VSEPR models and how it would look like. And with that, that's going to be it. If you have any questions, don't forget to message myself or Mr. Morgan. But other than that, stay safe, and I'll catch y'all next time.